So this week on the Spotlight Report, I am very excited to get to speak with Dave Aikens, who is the president and founder of Savvy Optics Corp., Eric Herman, who is a design engineer at Zygo. They are two co-authors on the book Modern Optics Drawings, the ISO10110 Compainon. And this is a really exciting book for me. I do a lot of opto mechanics in graduate school and optical design today. So it really bridges those areas in my mind. Can you guys talk about what the book is about?
Sure. Eric, why don't you go?
So the book is trying to take a lot of the information that's in ISO 10110 and the parts of the other ISO optics drawing, ISO standards for optics, and really make them readable for people, and distill a lot of that information so that you're not having to dig through, the words in standards, which can get somewhat confusing. And
I think for our audience, could you guys explain first of all, what is an ISO standard? And then specifically, what is this ISO 10110 that we've referred to?
Sure. So standards, when we're talking about standards, we're talking about documentary standards. So this is things like ISO 9000, people are pretty familiar with the quality standard, but there's literally thousands of standards from several different agencies. ISO is probably the largest. So if it's an ISO documentary standard, then it's been published by the International Organization for Standardization in Geneva. And one of the groups that publishes these standards is a technical committee, TC172, which is responsible for optics. And that committee published a drawing notation standard, ISO 10110. So this is a system of standards. It's a series of standards in parts based on DIN 3140, which is a German standard for drawings that was developed in the 50s. And so that became an international standard when it was published by ISO between 1994 and 1996.
And who uses ISO 10110? What would be a scenario? I mean, we're going to get into the meat of the book, but for people that aren't familiar, who would use this? Like, why would it be important, or when would it be important to use ISO 10110 standard?
So any user, should be somebody who's making drawings to get optics fabricated. It's a way to take the information that we need to make an optic and convey it in a simple way that it can be made anywhere in the world without having to deal with language barriers, and also get rid of a lot of discussions that you would have with a fabricator.
And I think that hits the nail on the head. Eric, you went to University of Arizona?
I did.
So please push back on me if you disagree, but one of the things that I came out of, this very prestigious college for optics was, all the theory, possibly how to do design if you take design classes. I took Jim Burgess' class, and he was my advisor for a period of time. So I had exposure to this idea that, in fact, at the end of the day, you have to make these things that you design. But even with all of that, I learned an insane amount from this book of things that you should classify, things that need to be marked up on your drawing to make sure you get what you actually designed. And this is something that plagues, I think, a lot of optical designers, this idea of like, okay, here, customer or boss, here's the system I designed. I think it's ready to get built. You get it back, something goes wrong, and you say like, I don't know. I don't exactly know what's wrong. And in my mind, ISO 10110 or using standards like this, and again, I learned a ton, help you get around that potential problem. So why did you guys write a book? Besides just for the fun of it, that's a lot of work. Why'd you make a whole book for this?
Well, so we were really inspired by a previous published guide. It was published back in the late 1990s, written by Bob Parks and Ron Kimmel. And it was the ISO 10110 guidebook. And it was published by OSA Press. It's been out of print though for, geez, probably 15 years at least. And it was way out of date anyway. The standard has evolved a lot from the mid 90s to the 21st century. So we were really inspired by the fact that this book kind of needed to exist, and we're constantly getting requests to rewrite this book, basically to republish Parks and Kimmel, and instead it was really Eric's idea to just motor through it and create an entirely new version, reorganizing it the way the book is organized. Instead of going part by part, it's grouped by topic, right? So it makes it a little more readable, a little less of a guidebook and a little more of a a little more like a book, right? A little more readable.
Yeah, and sorry, Eric, go ahead.
I was going to say, I mean, and part of that is, when you go and read through each of the standards, the individual parts of ISO 10110, they're put together as needed, but some might have come after others that you really that should be paired with each other, and so we can cover that more later. But yeah,
and I was going to say we'll put a link up to the actual standard, but again, for our listeners that are unfamiliar, what is it like? If I were to look up the ISO 10110 standard, what kind of reading am I in for?
Yeah, well, Eric and myself and Richie, we develop standards. We've been working in standards for a very long time. And if you work in the field, you learn this kind of special language that these standards are written in. And it's not English. It's a very kind of, they have their own set of terms that they have to use that are very specific to writing a standard, to standardizing things. So what you're in for, Logan, is some really heavy sledding. The standards themselves are put together by a committee. And it's an international committee, which means there's non-English speakers that are often project leaders for these standards. And the committee does its best, but they're only human, and they only have a few swings at the piñata for each standard, right? We go through a working draft and a committee draft, and then a draft international standard, and that's it, right? So we miss a lot. And there are lots of times when we just don't have the wherewithal to really rewrite sections to make it more readable. It's not the goal. The primary goal is to get the technical content right. And unfortunately, readability kind of takes a distant second place.
Yeah, that's something that really came across nicely in this book. As you've said, if I'm an optical engineer, not only if, but I am, but if I'm doing a design, when I finish it, I might say, oh no, I have to spec out this specific aspect of the system. I need to be sure it's built as such so it meets this requirement. And I've had times where I look up the ISO 10110 standard. Like you said, it's a very technical document, and it can feel a bit overwhelming, honestly, at the time when you finish your design, you've done your tolerance, and you're trying to kind of parse this thing and make sure, okay, I hope I have it right. And I think that you guys really knocked it out of the park on this book, in that it feels very much so like it was written for people in my position, where you say like, hey, this is a companion book. It's pretty easy to get all the way through it, honestly. Like we talked about earlier, I read through it start to finish. It's not bad at all, but just having it on hand, I think, is nice, because you can pull up, like you said, maybe I need to pull up the chapter on surface figure or whatever the case may be, and just reference it very quickly without having to go through technical documents. So, without further ado, why don't we kind of jump into what goes into an ISO 10110 drawing? And in fact, before that, what is this drawing? Just again, for people that aren't familiar, we've talked about, okay, I do a design and it's an optical system, and then I make a drawing. So if you've never done this, what is the drawing that we're talking about?
So the drawing is just some way that you're getting whatever you've designed conveyed to a manufacturer. And, there's drawing standards, not just for optics. There's, a bunch of drawing standards for mechanics and everything like that. And so this one is just taking all of the ISO 10110 is taking all of the tolerances and values that are specific to an optic and putting the and saying this is how you should put them on a drawing to convey to your manufacturer.
And,
Right,
and I'm gonna take it one more level down even.
Okay.
What is a tolerance then?
Okay, so ISO 10110 really is mostly about tolerances, actually. And what tolerances are is a description of the quality of an optic that is required for the specific application. So for example, you might be using shot NBK7 as a glass. Well, shot glass can have bubbles and inclusions in it. Are those permissible? And if so, how big can they be and how can they be distributed? So that is a tolerance. It is a bubble and inclusion tolerance. And ISO 10110 really is, it itself is a companion standard. It is a companion to ISO 1101, or what we use in the US, ANSI Y1415, which is a system of notations called geometric dimensioning and tolerancing, right? The problem is GD&T, or geometric dimensioning and tolerancing, doesn't have any notations for optics tolerances, for the things that we need to put in the drawing. So that's all ISO 10110 is, really, is a system of notations for the optics part of the tolerances.
Perfect. And I think that's worth mentioning because in my consulting work, you'll run into customers where they don't realize the importance of tolerances. They think that if you show them, here's the system as designed, that's what they'll get. And it can be a little bit hard to kind of convey this idea that this has to be made and it won't be perfect. We'll go through them, but you would mention some like bubbles in the glass or kind of dimension tolerances. It might not be exactly as thick as you want it to be, or it might have some wedge, tilt, etc. So, well, perfect. So I think that the first question that I have with respect to the book is, what are the primary areas that get designated out in an ISO 10110 drawing? Like what goes into the drawing, right? Can I just sit down and kind of draw my system out and then say, please make this well, or what actually has to be part of it to make it a formal ISO 10110 drawing?
So the ISO drawings actually have three broad fields in them, right? There is a drawing field, which is like the bulk of the drawing itself. And this is where you draw a picture of the component that you want or the system that you want. And there's some quirks and idiosyncrasies about optics, the optics version of that drawing. But that's sort of the top. And then there's the table field, which is where all the tolerances and notations show up. And then there's the title block, title field it's called, which is things like, scale and which way the views are supposed to be laid out and things like that.
Okay.
So those are the big chunks.
Those are the big things. There's a drawing, there's a table of information, and then, like you said, the chunk kind of describing it a little bit more. Mm-hmm. So you broke out the book. How did you break out the book? You mentioned this a little bit earlier, Eric, that you kind of reorganized it as well.
So each of the different tolerances that you would have on an optic, when you have them, some things go much closer together with others. So for example, the tolerance on optical form or figure, that's ISO 10110 part 5. But then there's another part for your transmitted wavefront, or what your system, effectively you could say your system figure would be, and that's ISO 10110 part 14. So those two standards really, they work together. there's describing very similar things with very similar notation, but when the standards were made, they weren't made one right after each other. And so having to, you know, group those things together instead of just by, you know, this is part 5, this is part 14, having to see those together, it makes a lot of the information much more clear. You know, and that was really the intent for us, was making sure you could go through go through and understand the standards to some extent and not just get overwhelmed by, okay, well, what's happening here? Why is it different from here? What's going on?
There's that's exactly right. And there is another whole layer to this, which is so that's ISO 10110. Parts 5 and 14 are both in the system of ISO 10110. But to interpret ISO 10110 Part 5, the surface form, you also need to look at ISO 14999 Part 4, which you know doesn't even have the same numbering system, right? So we pulled that in as well. And Eric was really good about making sure we had identified all the other kinds of standards that are going to feed into that optics drawing and understanding that notation.
Well, and one of the things I love of how you set it up is, to me, it felt very intuitive. So chapter 1, I had to pull it up. I didn't remember all the chapters, but chapter 1's drawing notation and default tolerances. Chapter 2, optical materials. Chapter 3, surface figure and form. 4 is surface texture. 5 is surface imperfection. 6 is laser damage. 7's coatings. 8 is centering and tolerances. And 9 is non-spherical surfaces. And the last couple of chapters, I definitely want to talk about at the end because they're more about testing. But to me, that was fantastic. You know, if I'm the designer and I'm thinking about it and I have to designate the tolerance for the material or the surface quality, those are the terms I think about, right? I don't think about the standard numbers. I think about materials. So it makes it really easy to kind of go through those areas as you need them. So just starting with the first chapter about kind of dimensional tolerances, I want to start with what is included in that and what's not included in the ISO 10110 standard. I mean, Dave, you mentioned that you kind of have to pull in some other standards for some of these things. So what's not included and where is it relevant?
Let's see. Not sure I understand the question. Eric, did you?
Well, I think that there's some interesting, you had mentioned, I think that thickness and diameter is not formally part of ISO 10110, but it seems like it's obviously a key designation for a system. So are there any other, major areas like that for the dimension where you think, of course, this must be part of the standard, but in fact, it's not?
Yeah, well, so chapter 1 really draws from what used to be parts 1 and 10 in the ISO 10110 system, which was assuming you're starting from ISO 1101, so you're making a mechanical drawing. What special rules do there need to be for optical components and optical tolerancing? And one of the probably the most obvious to any mechanical engineer is when you get an optics drawing, an ISO 10110 drawing, most of the time there is only a single view, and any mechanical engineer can tell you you can't do that. That's not allowed in GD&T. But in the optics world, if you just draw, and it's not even a view, it's actually a cross section, right? So we have this cross-sectional view, and now that's just traditional throughout optics, both in Germany in the DIN 3140 system and in the United States in the ANSI Y1415, or even before that, the MIL standard 34. They've always allowed this cross-section view as the only view if the optic is rotationally invariant, and there's no need for a second view. You can explain everything in that single picture. And then, so that's sort of one of the aspects of chapter 1, where we go into what the format of the drawing actually has to be. But anything basically that you can specify using GD&T, you can use on an ISO 10110 drawing, right? So you don't have to just draw from this one system of notations. You can put on, dimensional tolerances, minimum material conditions, whatever, all the rules that you have in normal mechanical engineering.
Right.
You can draw from
they're not excluded from the drawing.
Right, exactly.
Okay.
But there are special rules that that only optics drawings are allowed to do.
Okay. And you hinted at something pretty important, which is historically optics were circular, spherical, possibly aspheric surfaces, i.e. rotationally invariant. If I look at it from the side or the top, it's going to look the same. And you address this in some of the later chapters that as we're increasingly moving towards freeform and more peculiar surfaces, that might not always be the case. So in this drawing, you cover this in chapter 1, but is it a lens? Like when I make a drawing, am I going to make it just of a lens for every lens in my system, or will it be the whole system?
Well, used to be there was only a lens for every drawing. And then there was you had the ability to create an assembly drawing, which was meant to be a way to write down how to cement a doublet or something, right? That was the original version in the 1990s. As the standards have grown and developed, it's added all sorts of other features to allow you to actually specify the entire system. And one of the things that Eric did that I thought was really just brilliant was the entire chapter 12. I mean, he basically wrote that whole thing himself. It is a beautiful walkthrough of a system, which takes you from the requirements to a system layout, and then the individual component drawings as well. So that becomes kind of a drawing package, right? The overview of the system, and then the individual element drawings you could send to optics manufacturers.
Yeah, and I definitely want to talk about those later chapters because they're really, really valuable. But before we get there, you allude to this in chapter 1, but I think it's important for listeners to be aware of. There's a variety, even for the dimensioning tolerances, there's a variety of tolerances, right? As we mentioned, diameter, center thickness, that's not even getting into the tolerances of later chapters. Are those tolerances different, or are they kind of unique per surface? So if I'm making a spherical lens, for example, is that going to have kind of tighter or looser tolerances than if I'm making perhaps a freeform surface or a molded optic or whatever the case may be?
So, I mean, again, those tolerances, those values are going to vary just based on how you've designed your system, how it's, that you've toleranced it itself. And so having the variety of, just in that first chapter, and it really in ISO 10110 part 1, just this is how you would define this tolerance. There isn't much more past that than just this is how you do it. And a lot of the other nuances of, let's say you're working with a freeform versus just a normal spherical lens, that's something that you're going to have to handle when you do your tolerance analysis and when you're, deciding to make that lens. Before you even.
I guess a follow-up question is there any downside from my perspective if I say, well, I really want to be sure that this is made right, so I'm going to set the tolerances super tight?
The big difference would be cost. I mean, your fabricators might be able to, you might get pushback at some level of, hey, you can't get this, or if you want this, it's going to be X times multiplier more. It's going to be your cost with a lot of those things kind of scales. And so having, this is, you have to have some idea on what sort of tolerances you're going to be putting on a drawing. Yeah.
And I think that the tolerances is like a really key part of the optical design. Logan, you and I both do consulting. Eric's a full-time optical engineer as well. So I can speak from my own experience. I might spend a third of my time doing actual optical design and 2/3 of my time doing the tolerancing and manufacturing support. It's an enormous part of the job that I agree with you. A lot of my customers aren't aware of that part of the job, right? So yeah, the just cranking out a lens design in Zemax or Code 5 that's just the beginning. And those tolerances and understanding them, that's the bread and butter of an optical engineer, in my opinion.
And I think that that's something that I kind of want to get at, because Eric, you're being almost too generous, perhaps. I've given some truly crazy tolerances, fortunately, when I was still taking classes. So the only person that laughed at me was Jim Burge, saying like, "Oh man, you need to learn this before you hand it to a fabrication shop, because you know you'll lose some face at that point." And you allude to this, that in chapter 1, it's laying out how you're going to state these tolerances, and the other chapters describe the other ones. But where do I even get that idea? Is it just, Dave, is it just something that you've learned over time for these are realistic tolerances that I could apply? Or where does one kind of get that knowledge?
That's a great question. It really does come over time. There's no question that experience is the best teacher here. I had some specific events that occurred in my life that taught me an enormous amount about tolerances, especially tight tolerances. And if I can tell you a little story, I was a young consulting engineer working for an aerospace company in the Pacific Northwest. And I had designed a new FLIR system, so long wave infrared. And I had specified I remember the primary mirror was specified to a 0.005 of an inch on centering tolerance for the objective lens, right? So this is like an 8-inch diameter lens. And it was mounted on a helicopter, and a helicopter landed on the gimbal and smashed the system. And the service manager called me in to see this system, and he'd gotten it up and running. The objective lens was off, right? And there's a big chunk missing in it. And he very carefully goes through the drawing and says, "So what's that centering tolerance there, Dave? Half a thousandth of an inch. Let me just see what happens." And he holds the lens in front of the imager, moves it around with his hands, and it passes its MTF test. So that really taught me that I needed to be much more careful about really thinking through what I needed to have before I just, pushed that all downstream to the other people. But I wanted to mention one other thing, which is one thing that is really lovely about ISO 10110. I think it's the thing I found most elegant when I first started using it back in the 90s, is that it is a notation system that is really tailored to make sure you don't miss anything. And in fact, there's an entire section, part 11, which is what does the manufacturer do if you forget to put something on the drawing, which I think is just delightful, right? It's called non-tolerance data. And so this is a way where they're not really super tight. They're actually really quite loose, but it's nice to have that document, because you can look at it and go, oh, okay, so if it's, if it's 0.025, then that's not going to be that expensive. And I can, probably buy it because it's the default tolerance, which we know is necessarily loose. So you get this tolerance backstop for free in ISO 10110, which I think is really powerful. But you also get sort of a checklist of, this is what loose looks like, right there in that standard. And you can kind of go, oh, okay, so these are loose tolerances. So figure a factor of 10 tighter than that's probably going to be pretty hard to do, right? Mm-hmm. So it's kind of a nice bellwether.
Yeah, and I mean, as you said, there are a lot of tolerances. Even just going into, chapter 2, optical materials, it's material properties or refractive index, stress birefringence, bubbles and occlusions, homogeneity, striae, and that's just 2.3, right? So there's several sections in chapter 2. And I think that's a great point, that like, if you miss something, there is still a backstop. It's not just up in the air of like, however I make it, I make it. And I love that story, Dave, because in consulting, the consequence of setting too tight of tolerances is the customer that's paying you is going to pay way too much, more than they need to. But they might not know. And I think that it's really important. It's almost a responsibility for the optical designer to make sure that they're not passing on unnecessary costs. So in my mind, it feels like, hey, it's on me. I shouldn't mislead you. And conversely, if I don't set the tolerances appropriately or too loose, whatever the case may be, it doesn't work. And often the customer will be upset in general. And I've had customers come to me to say, why doesn't this work? You didn't do the design, but why doesn't it work? And in some cases, oh, there was no tolerance. There was no GD&T done, period. It's just, here's a system. So that makes it a little bit easier. Is there kind of a different, is the same thing true, I guess, in industry? Just in the general scenario, are the motivations for getting GD&T accurate similar?
Eric, you want to take that?
Yeah, I mean, I think, you know, it's just a yes, you know, you want to, you know, I don't know how to expand on that further, because, you know, with a lot of GD&T things, when somebody's making a mechanical drawing, a lot of the time, you know, that there are a lot of tolerances that you would put on a for, you know, a piece of metal, that, you know, your positioning tolerances, how, you know, flat, you know, things are, how concentric. So those are, you know, things that typically are being thought of along, you know, that when those parts are being designed, at least to some level. And so, you know, it's the same thing with optics of, you know, you kind of have to get these things right when you're making that.
Yeah.
I mean, the right guy to answer that question is our third co-author, Richie Youngworth, who couldn't be here today, right? He's the cost of tolerancing god. So, you know, he's, in fact, we co-wrote a paper with Jessica Nelson at Optimax about the cost of tolerancing. It was just about this one topic. But I think his thesis was in this area, wasn't it, Eric?
It was all on tolerancing.
Yeah, I mean, so he's really the guy.
Sure. And I just think that one difference in my mind, and please push back on this, but in my mind, consulting, it's kind of like a do or die scenario. You don't, it's an engagement, and it's going to begin and end, and you hope that they're satisfied at the end and they didn't pay too much and they get something that works. And in my limited exposure to industry work, hopefully they're not going to fire you if you mistolerance something. And I think that the consequence is, if you're doing things too tight, presumably you're on a team and someone's going to notice and say, pump the brakes a little bit, right? You're costing the company time and money. And conversely, right, if you're not setting them tight enough, there's usually a discussion to say, why are things going wrong? But I think you have a little more wiggle room, possibly. Maybe that's not always the case, where you can kind of learn over time how to appropriately set these tolerances. Maybe that's wrong. I don't know. I don't work at a company, so maybe I'm being optimistic here.
No, I think you're right. Well, one problem that occurs in industry and maybe in consulting as well, actually definitely in consulting, is you don't get to see the ending a lot, right? In consulting, you do your job, and, you know, my wife's a musician, so she would say, I just leave my music on the stand and go home. And that's what we do in consulting. We finish the design and we hand off, sometimes not even drawings, just the information about the system, and somebody else takes it from there. In my first job, I was at Hughes Aircraft Company in LA, and right out of school, I had no practical experience, right? And so they assigned me a mentor, and that mentor actually met with me once a week and kind of showed me the ropes. And that went on for like a year. And it was a really great opportunity to learn and get that backstop you were just talking about, Logan, where, you know, my mentor is going to review anything before it goes to a vendor. But the problem was, from the time that I would do my work to the time that they would build something was so long that it was difficult to learn from your own mistakes, right? And I think that exists in industry writ large. It takes that time lapse in optics, starting with the optical design and ending with hardware, that can be a really long timeline. And so it's difficult to learn from your mistakes. And my second job was actually at Lawrence Livermore Lab, where I would design something and we would build it the next week, right? And that was a totally different experience. I could really learn that, you know, as I'm fond of saying, ZMAX lies, code 5 lies. It's just, you know, you can do it perfectly in the code, but that doesn't mean you can build it. That doesn't mean it's actually going to make an image.
Yeah.
So, and I think these days it's getting easier, right? Because that timeline is shortening just industry wide. Everything's going faster now. We've got 3D printing, 3D printed lenses even. So I think maybe you've got more of an opportunity to learn from your own mistakes, but nothing can replace that mentorship thing, which is much more common in industry and doesn't really exist in consulting, right?
And no, absolutely. Unfortunately, one thing that I've heard of that I wasn't fortunate enough to experience is I've talked to some people at companies where they say like, look, we have a fab shop, like we work with this fabricator, and it's nice because you, in their words, they develop this relationship over time to know here's the tolerances that they're going to expect and what they can hit. And you can learn from the other side, right? The side that you're really trying to communicate with. Mm-hmm. So, all right, I've skirted around this for too long. I apologize, but let's move on through the book. Chapter 2, optical materials. Why would I spec that out? I do design, right? I state the shape of the surface. I make my perfect lens. Dave, ZMAX and Code 5, they never lie. It'll form a perfect image. I don't care about the material. I just, so long as it refracts it correct, that's fine.
Yeah, right. It's shot BK7, right?
Yeah, exactly. It's right. It's 1.5, refractive index, whatever. I'm good. So why would I spec out optical material parameters?
Because what you're going to, again, shot BK7, you're not going to always get exactly what you think. There's always going to be some deviation from, what they're going to make. And that's, more than just batch to batch. It's also, if they're making a, strip glass, one part of the strip might be very different than the other. And so, setting those tolerances is making sure that you're at least getting what's good enough for the shot BK7,
And what goes into that? You part of the ISO 10110, it's refractive index, but it's also bubbles, homogeneity, stress birefringence. What does this mean? Like if I get a really bad material, what do I end up seeing? How does that impact the system?
So it's going to be different, things at different points. So, bubbles and inclusions, you might, they're going to be, within that part. And so they may be something that you can visually see with your eye. It may not impact your optical system too much, but it's still something that will have some effect. Stress birefringence is when they're actually melting the glass and going through, and if they're not annealing it properly, you're going to have that, those sorts of, stresses that are going on, and you might end up having, polarization issues because of your glass in particular. The homogeneity is just what is the refractive index through the part? Is it going, how much is it going to change? And your stria is, what if it is going to change for refractive index, what sort of, how much is it going to change it at some given period, in frequency?
Mm-hmm.
Spatial period.
Yeah.
And basically, in my mind, it's unfortunately, again, things that we, in my experience, people that kind of went through standard optical engineering don't think about as much. You're not totally as clued into like there's bubbles in the glass,
right?
Let alone what those do. You don't see it often, right? Like the lenses that we deal with, you look at them, you don't see any bubbles in, often. So it's hard to kind of physically think about how this would impact something. Non-homogeneous materials, similar thing. But they have a huge impact. And at the cutting edge, these people demanding good products really care about some of this performance. And so, right. And so moving on through the book, chapter 3 and 4, I love. I love it because my dissertation was on metrology and measuring surface shapes. And chapter 3 is titled Surface Figure and Form. And chapter 4 is titled Surface Texture, Roughness, and Waviness. I'm going to keep trying to play the totally naive designer, and it's pretty easy for me, honestly. What is the difference between surface figure and form and surface texture? Like, I don't get it. Why would there be any difference between these things?
It's all a matter of scale, right? So the surface form is the shape of the surface on a large scale, and we think of form errors as covering the entire part. So maybe a little bit of changing curvature. The spherical aberration shape has kind of a fourth order function to it, right? So that's form errors. And texture, well, roughness is easier to describe, right? Roughness is micro roughness. It's stuff going on a very fine scale, like microns, right? Not the whole part. And then waviness is the stuff in between. So defining where roughness ends and waviness begins, or defining where waviness ends and form begins, is actually really application specific. Each application and each lens might have a different boundary for those conditions. And in the lithography world, what they call waviness, most people would call roughness, right? They go way down into the really micro spatial frequencies, and they specify how much undulation you can have all over the surface. Whereas in conventional telescopes, roughness goes all the way up to like a millimeter or two in scale length. So it really totally depends on the application.
And I think part of that too ties in to some of the later chapters, which is alluding to the idea of like, how are you testing them? That has some implication as well. So, there's so many chapters and we have limited time, so I have to pick and choose what we're going to cover. But how are some of these things tested? I really loved chapter 10, 11, and 12. I love that at the end of this book, what you did was you said, chapter 10, system evaluation. This literally blew my mind, right? I have a PhD in optical engineering. I've done optical design. I'm almost embarrassed, but also very happy to say that this chapter was just like revolutionary for me, because it discusses the tests to measure certain things about a system. Chapter 11 talks about environmental testing, how I might test my system in a variety of scenarios it could be in. And then chapter 12, as you said, was standard and practice. So I'd love to just hit these, and unfortunately we're going to have to skip over some of the other tolerance areas. Laser damage, obviously a key one depending on your applications. Surface treatment and coating, again, very important. And there's a few others, but just going to chapter 10, system evaluation. What does this mean? Like, what is a system evaluation, and why would that be important?
So a lot of this, the stuff that we've been talking about, for those individual tolerances. So that's, how do you make one, aspect of the part? So how well does it need to be, have the same radius that you want, all those sorts of things. But when you actually go and start putting your lens together, how are you going to say this is good enough? So, as optical designers, there's usually some figure of merit that we're working towards. And so, with imaging, you'll see, it needs to have, X resolution. And so as you're going through, one thing that, most people do is they just they have their own tests, or they've thought of their own tests for doing those sorts of figures of merit. But within the ISO TC172, as well as actually another TC, they've kind of gone and standardized a lot of these tests and said, great, you want to test MTF, this is the way to test it. And you're going to go and, have your test set up this way, and you're going to do these different things. And this is going to be the end result that how you're going to evaluate it. And so there's all of these different tests that you can have and you can do, but you know, putting them all in one place is really important for somebody to think about.
Well,
Yeah,
and
when,
it
just so I could jump in here, that when Eric proposed we add 10, 11, and 12, which wasn't in the original Parks and Kimmel, right? I was extremely skeptical. I was like, oh, come on, environmental, fine, whatever. But, you know, when we were doing it, I think I enjoyed 10, 11, and 12. Writing 10, 11, and 12 with Eric and Richie was a blast. It was really fun. And I had more fun with those 3 chapters than the rest of the book. And I also learned an enormous amount, right? I had no idea there were all these standards for veiling glare and transmittance and all these other standard testing methods that just, you know, I knew about a few of them, but I didn't know about the vast breadth of ISO standardization for metrology. I thought it was really awesome.
But I'm glad you said that, and I'm not the only one. Chapter 10, I literally texted friends. Yeah, you guys have to check this out, and they probably said, "Oh man, Logan, I don't know if I should be friends with him anymore if he's texting about optics books." But you lay out some of the things. It was, you know, wavefront error. How are you going to measure wavefront error? How are you going to measure resolution, distortion, transmittance, stray light, and relative illumination? And one big issue that I have, and it actually was a key motivator for Isaac and I in starting our own company, but an issue that I have is that design can be so kind of dysregulated from getting something made, right? You know, it's hard for design, like you said, Dave, you spend a third of the time on design and 2/3 on making sure the tolerance is correct and that information is conveyed. And that leaves out even the other final aspect, which is, how do I know it was made right? And again, you know, I study metrology for my dissertation work, and I almost think that was a bad thing because, like you're saying, I can think up all sorts of ways to measure these things. You could set up this test or this test, and the idea that you're making something, you're designing something to get it made to work. I really love these tests because it kind of changes, I think, the way I'll do design work in the future, which is to push on, for customers and consulting, this is obviously different in business, to push on them the idea like, here's what we can measure and how we can measure it, and it's unambiguous. So your requirement should hopefully slot into these areas. Anyways, I cannot recommend that chapter enough to anyone listening. What about environmental testing? Why would I need to test this? And what is the environment? What does that mean?
So for environmentals, at least, you know, for me, earlier in my career, I'd done some work for space-based systems. And a lot of the time with that, you're having to deal with so many different, you know, you may make your optic and that's fine, but you have to go through so many different environmental tests to make sure that it's going to be okay. And, you know, within our ISO TC 172, there is a whole separate working group just on environmental standards. And so when we think of, you know, I guess, you know, ISO 10110 on its own and doing everything, it's very much in a vacuum, but there's all these other groups that are to the side. And so doing that environmental testing at the end of the day is something that a lot of people are going to have to do. And making an optic isn't in a vacuum. There's, you know, as you said, you know, you have to think of how you're going to measure it along the way. And so if you're going to have to operate in some, you know, weird environment, or, you know, if you're going to have to, you know, have this thing work, you know, while you're on an island next to the ocean and, you know, you're getting hit by salt water, those are things that you're hopefully going to want to test for, or at least make sure that it works in that regard. And so for chapter 11, a lot of it was just, I want people to be aware of these other things to consider when they're thinking of making a drawing. It's not just, cool, I made my lens, I'm done, here, you're on your own.
And is vibration testing, is that part of the environment?
It is. Yeah.
So one of my favorite stories is that I have a friend who's an optical engineer, who I look up to quite a bit. They're very, very smart in optical engineering. And I recall one time they had spent a good amount of time building a very custom system. And their customer expected it to be, I want to say deployed in like a helicopter or something, for example, and didn't give a spec on a lot of things. And
Shake and shock.
yeah, and I was talking with him, we were grabbing beers, and I think that it kind of occurred to him, he's like, oh man, we need to test how stable it is in vibration, and we need to deliver it like ASAP. Like everything was good to go, they need to deliver it. We don't have a vibration test device. So they put it on one of those lab carts, the plastic carts, and rolled it across the parking lot, which is very gravelly and bumpy.
That's a great idea.
Yeah, right. I guess better than nothing. So you close with, well, actually, you have an epilogue, but the final formal chapter is standards and practice. Can you just kind of give a higher overview of what this chapter is?
Sure. So, we've gone through every other chapter in the book, go through and explain each of the parts of ISO 10110, and this is how you specify this or that. But at the end of the day, what are you really doing with this? I can tell you, each of the little nuances of things, but how are you really going to, take this standard and really use it? And so that was a lot of the motivation, was if I'm somebody who doesn't really know what I'm doing with this standard, let me walk through and explain where I'm pulling different things from each of the different chapters, and let's build this system along the way. So, we started with just came up with some base requirements, between Dave, Richie, and I, that we discussed and had a design and said, okay, we want to make sure that we're going to cover 3 different types of drawings. So for the lens in question, it's we have a doublet, an A-sphere, and a normal singlet. And so making each of those 3 drawings, we want it to be, they're all different in their own regard, because each one uses different aspects of ISO 10110 where others may not. And so you taking each of those 3 parts and, great, I now made my drawing for each one. Well, how am I going to get this thing together? When we first talked about this chapter, there was a set of requirements. Well, how are we going to meet those requirements? And as, we just talked about in, chapter 10 and 11, yeah, there's all these different tests. So let's actually make a drawing that has all of those things together, so that if I were to go to some shop or whatever and say, here's my package of 4 drawings for my 3 parts and my assembly, they should be able to go and assemble it and give me a finished lens that would meet those requirements. And so again, it's just trying to take all of those different things together so that somebody who isn't aware of making an optics drawing can just go, oh wait, so that comes from here. Okay, now all of these dots get connected.
Yeah, I view it as almost a walkthrough, right? It gives you, like, I don't know if you've read Modern Lens Design by Warren Smith. It's a fantastic book. But my favorite part of Smith's book is his walkthroughs, where he does a triplet from scratch or a Tessar lens from scratch. And I really saw this as tying the whole book together when we did it. And Eric did a great job on the kind of the process that you would naturally go through to figure out what to tolerance and how to specify it. And so I think, for a lot of people, you could almost start with chapter 12 and then go back to the different sections that you want to read. But yeah, chapter 12 is a must read. I think it's a fantastic section.
I do think that's a good recommendation, that the individual chapters, you can dig about as deep as you want to find the specific information you need. But chapter 12, I don't know why it's so rare in optics to have these like clear guides. Here's something you have to do. Here's how you do it. We're just going to walk through it. So Thank you for providing it, because it really is extremely helpful. Well, that covers the book, and I want to ask a question that someone else actually put forward to me, but in general, they were saying, for freeform optics or diamond turn machines or computer controlled fabrication machines, you pass in some digital version of your design. The computer guides the machine, it fabricates it, everything's good, and it's digital and modern. And basically his question was to say, does anyone use paper drawings anymore? Does anyone even use ISO 10110, right? Like, if everything's so modern with computers, is there a place for ISO 10110 drawings? I know the answer. I know there is, but I want to hear your guys' statement on it.
It's a good question, and I've been asked this question before too. So, in the mechanical engineering world, things are moving very quickly away from drawings and towards models, right? You just send the model, and the tolerances are in the model, and that goes to the machine shop, and they just make the part. Optics is actually a little behind on this. We had some opportunities back about 10 years ago to try to come up with a standardized method of describing all the tolerances in the model. And we really, and so there is a standard called no diff, which is supposed to be a system that works kind of like STEP, but for optics. That's the idea. It isn't broadly used though. It's a bit unwieldy, and it's not really written in a format that, it's not like an XML or something. It's not in a real actionable form today. And this has been, we've been discussing this in the committees actually recently. So the group that Eric and I work in, and Richie as well, is SC1. In fact, Richie is the chairman of SC1 now. He chairs the international meetings, and it's broken into 4 working groups, actually 3 working groups. Working groups 1 for metrology, 2 for drawing notations, 3 for environmental that Eric had mentioned. And that committee is considering spooling up a 4th working group just to focus on this issue and come up with a way to transfer all of that information in an electronic file, so you don't need the ISO drawing anymore. We're not there today, and so today, I think in standard practice, you email an ISO 10110 drawing, and the manufacturer marks it up and sends it back to you, and that's the method we use to figure out what part to make. But yeah, someday I think ISO 10110 could just be, the digital version will be the only one that anyone cares about. There's a little bit of history here too. ISO 10110 was based on DIN 3140, right? DIN 3140 is a pictographic system which had just a drawing field. There was no table field. It was just a drawing field, and you indicated with leader lines the surface tolerances for the left surface, the right surface, and the material. And when ISO 10110 was first published, they published a part 10, which was tabulated drawings. And this was meant as an alternative method, as a shorthand, right? Because you pulled all that stuff off the drawing field and put it in this table field, and it made it easier to read and understand and keep track of things and whatnot. That's now the standard method, right? In 2019, I think it was, we merged part 1 and part 10 into a single standard and flipped the order so that now the table drawing is the preferred method. And the vast majority of ISO 10110 drawings use that tabular format, right? So I do envision, probably not too long in the future, where we'll have another version of ISO 10110, which is the electronic version, and where all that information just goes in the file and gets sent to the vendor. But it's still a ways off.
Right, and I think that's an important thing that you added as well at the end. There is this is a living standard. It changes. Maybe not all the time, but it does change. And for the time being, you make the mechanical drawing, and I think it serves a dual purpose, not only to assure you get the thing made correctly, but also just documentation is a huge value of it. So Two final questions. I know we're about out of time, but just very briefly, I'd love to hit on first the idea of how do you hope to get more people using it? How do you hope to really kind of convince people it's worth your time to make a proper ISO 10110 drawing? And before you answer that, because I think your answer to this other question might address it, what's the benefit? What's the benefit if I go through this book, if I hadn't, if I'm an optical engineer and I went through this book, what do I get out of it? I have my own answer, and I'll add that at the end, but I'm curious what you guys see as the takeaway from it.
Well, as far as getting people to adopt ISO 10110, I think this podcast is part of that, right? This is sort of outreach. And Eric, Richie, and I are all really active in standards development, but we're also really active in getting these standards drafted and getting them used in industry. In the ISO world, an ISO standard has no power per se, unless it has been adopted by a member body. So the United States needs to adopt ISO 10110. So the next thing on the list is to take this ISO 10110 standard, which I think has come a long way from the 1990s, make that an American national standard. And we're in the process of doing that now. So we are publishing an American national standard version of each of these parts. And that's going to, I think, really increase the exposure in the US. And the other thing that I personally do for the outreach bit is I actually teach a class in how to make an ISO 10110 drawing. We recognized a long time ago, these standards are difficult to read and difficult to use, and you sort of need a guide, right? And so I became a guide for people if you're doing a rollout, and I'll come and teach all your mechanical engineers how the notation works, and they get a nice big book that explains that in PowerPoint form, and then we'll go through some drawings together and watch a conversion from a mill standard to a ISO standard. And Eric had the idea a couple of years ago, well, we should just make a poster of a drawing, an ISO drawing with bubbles coming out of it that explain all of the stuff that's in your course. And so we refer to it as the decoder ring poster, and it's available on the OEOSC website. You can download it for free. And I think it's fantastic. It's just, it should hang on the wall of every optics company in the world, in my opinion. It's just fantastic, but certainly in the US.
And we'll put a link to that in the show notes as well. Yeah, my takeaway is kind of multi-tiered, but at the very, very base level, I'd say if you read this book, you're going to be a better optical engineer. You're going to have better odds that the thing that you design actually gets made. And that's it. That's your career, right? So there's almost nothing more valuable. I would go even a step further though and say, I think that you gain a lot of peace of mind. You gain the ability to say, like, I spec'd out what I'm anticipating is going to happen, and it's documented and it covers my bases. So there's nothing up in the air to say, like, yeah, I think I did the design right. I think I marked everything up right. Fingers crossed. I hope it's good. It really makes it unambiguous, which I think is a huge value. And in my opinion, kind of any level of engineer could benefit from this. Like you said, an intro engineer, start in chapter 12 and see what you're not familiar with. But even a highly experienced person, just being able to kind of reference in on the chapters is super helpful. Well, the last thing I guess that I'll go ahead and ask both of you is, what's next for you guys? Any new books, or are you going to take a break from writing? I know, Eric, you push for extra chapters, so are you trying to start your writing career off, or what?
So I think right now the biggest thing has been, because of this book, we found that so many different parts of the ISO standard are interconnected. And so I think we've been trying really to, that most, outreach papers that you've seen from the US have been, here's ISO 10110, use ISO 10110. And going through this, we realized wow, there's so many other things that are related. And so the biggest push as of late has been really doing environmentals and starting to try to focus more on the coding side as well, because the coding world, it's its own world that unless you're in it, you don't think about it. As an optical engineer, it's a coding, go do it. But because it's so interconnected with the rest of the optic, we've really kind of been like, all right, well, we should actually start looking at these other things. And so right now we're trying to pull a couple papers together on more of those side environmental coding things that you wouldn't have that we wouldn't have been thinking about before, just other than here's my optic, let's get it made.
Yeah, if you just bought ISO 10110, you wouldn't know the coding stuff is all in 9211, for example, right? So
Yeah.
they're all interchanged. The thing I would say, just to add to what Eric said, is that I'll be more blunt than Eric is. When we were writing this book, we found glaring errors in ISO 10110 and in all the ISO standards. Huge issues where they don't quite seem together, that this standard says one thing and the other standard doesn't have a notation for it. And so I think the next 5 years go into fixing all the things we found that are wrong with the system as it is. And don't get me wrong, ISO 10110's come a long way from the 90s. It's an excellent system. It's very usable. It's really a great standard. But as we explored all the connected standards, we found there's plenty of work to do to put some notations in that are missing, and to put some a little more technical meat into some of the testing standards. And so that's sort of that's my view, is Richie, Eric, and I are very active in standards and standardization, and I think we're going to spend the next few years fixing all the things we found that we want to fix, right? And that means all new revisions of all these standards, and that means the book's going to be out of date. So then I think we go back to writing another book. So
version
my
2.
take. Yep, version 2, exactly.
Perfect. Well, Dave, Eric, thanks so much for taking the time to talk. The book, again, is Modern Optics Drawings, the ISO 10110 Companion, which you can buy on SPIE's website. There you go. There's the book. Thank you. I only have a digital copy, so I was trying to think. I can't quite hold it up.
Yeah, I can't hold it up. It disappears.
Right. And we'll provide a link to that as well in the show notes. But again, I can't recommend it highly enough. So Dave, Eric, thank you again.
Thanks very much, Logan.
Thanks.